I just one more video before I lose power here. Let me pull this up for a second. Let's go back to this. Yeah, I just wanted to show you a little bit of a Minitab simulation here and how a confidence interval, well, not really how it's constructed, but the idea of what it's telling you. So I have an ability in Minitab to generate random numbers, okay? And I can choose the random numbers to come from any distribution I would like to. So assume for this simulation that I have a nice, it's not drawing, there it is, a nice normal distribution, center at 0 and sigma of 1. Okay, so in other words, I mean, imagine pulling a random number from there. Most of them are probably going to be between -2 and 2, or within one standard deviation. So all I'm going to do is ask Minitab, generate for me 100 values. So generate like an x1, an x2, an x3, 100 values from a normal 0, 1 distribution. And I don't think the numbers will be surprising to you. So I'm going to open Minitab here, and I think it's under calculate. Yep, random data. So you see there's a ton of distributions. So generate data from a normal distribution. Number of rows, let's generate 100 rows of data. Let's store it in C1, the first column. So I could have any mean and any standard deviation I want, but I'm saying take it from a bell curve with the center at 0, standard deviation 1, generate 100 random values from that distribution. So they're coming, and there are the values, and you see 0.86, 0.06, 1.7, 2.1, -1.78, and right, I mean, most of them are between -2 and 2, I have to think. I mean, if we got something beyond 4, that's pretty unusual, right? I mean, to be beyond 4 standard deviations, but we could actually list them from high to low, but the bulk, right, 95% of your data is within 2 standard deviations, so probably most of the data is within there. We can do in Minitab descriptive statistics, so I can just say, hey, display the statistics from here, so variable is C1. What statistics? Let's get the mean, standard deviation, min, max. That would be nice. We don't have any missing. There were 100 total. Maybe the median when we line them all up and look at the middle point. So let's tell Minitab okay. And so it tells us the mean was, this is x bar, little x bar for our sample out of this entire population. And notice that we know the mean is 0, but we actually got 0.1. The standard deviation, we set it at 1, but you can see it's 0.909. It's not going to be exact. Here was the minimum. Here's the median, very close to the mean. Not surprising because I have a symmetric distribution. Max was 2.1. Okay, so nothing too surprising with that. Okay, let's go back to our data. If I was going to make a confidence interval, what I'm making it from actually is the mean. The mean is going to be the center, right? That's my estimate. And then I'm going to go off in both directions around the mean and build a little interval for myself based on the standard deviation. So I'm going to use the mean, the standard deviation, and also the sample size to construct these. So right now, let me just generate another, this is going to seem weird, but I'm going to generate 100 columns of normal 0, 1s. Okay, why not? 100 of them. So let's see, calculate random data from, where's normal? Here's a normal. I'm going to generate columns C1 to C100, and all of them I want to be normal 0, 1s. Okay, so this column has 100 values in it, normal 0, 1s. This has 100, 100, 100. Each of these columns I'm going to build a confidence interval. Now Minitab will do that for you, and I'm not telling you how to construct it yet, but I want you to take a look at these intervals. Basic statistics, one sample z-test, sample in columns C1 through C100. Standard deviation was 1, and I want to make confidence intervals. Let's do maybe to make a point maybe more clearly. Let's make 90% intervals. So I'm 90% certain these intervals will contain the true mean mu. And we know what the true mean mu is because we're the ones that generated the random data. So let's see how many of them actually do contain the true mean mu, which is 0. So let's go up here. And you can see over here 100 data values. There's the mean, there's the standard deviation. Okay, so here's the confidence intervals that were made. This one contains the true mean mu, which was 0, so one of them does. 2, 3, 4, 5. Now look at the sixth one. I think that's the sixth one. I mean, the point is right here, you can see that this guy right here does not, it's the top one there, does not contain 0. So there's one confidence interval that doesn't contain the true mean mu. So let's keep going. There's a second one. It's low, doesn't contain mu. And you can kind of see why this is happening. Look at the mean. The mean is pretty far away from 0. So when I put a little interval around it, I'm not capturing 0. So there's 2 of them so far. Let's keep going. Here was another one. There's 3. Just looking. Now here's another one. Well, I don't know if I counted this one. I don't know. Either this is 3 or 4. And here's another one, 5. Here's another one, 6. Here's a 7. Here's an 8. We're already at 8. We only have 50 trials. Here's another one, 9. 10. Surprising we're missing most of them low, which is not necessarily supposed to happen. 11, 12. I'm just most amazed that most of them are low. I don't know why we only have, oh, here's another, so here's one high, 13, we missed it. 13, so right there, that is a good idea about a 90% confidence interval. If I make 100 intervals, I expect about 90 of them to contain the true mean mu. There's always that chance you're not going to get, even though you take a random sample, you're not going to get an X bar that will allow you to capture mu when you put the standard deviation around it. So if I had built 95 percenters, I'd expect about 95 to contain mu. If I had built 99 percenters, about 99 of them should have contained mu. So the thing that's random, I think a lot of people think a confidence interval is not random, it's solid. The thing that's solid is mu. Mu, somebody knows mu. Mu is known. The thing that's random is the interval. Every time you get a new random sample, you're going to get a new interval because you'll get a new X bar, you'll get a new standard deviation. So that's the main point I wanted to show you there. So let's go back to the lecture. So what I did is I made 100 observations of a normal 0, 1. I did this for 100 different intervals, and I built 95% confident. Well, I actually built 90, and we saw that only about, well, 13 of them didn't have mu, and about, 87 did. So if we had built 95ers, then approximately 95 of them would have contained the true mean mu. When you build it, you have to be thinking, if I build a 99% confidence interval, I'm 99% certain I've captured mu. And the more certainty you have, unfortunately, your interval is going to get a little bigger too, just to be able to capture mu. So this is just a reminder here that mu isn't changing. Mu is a given thing. I mean, for even the true mean GPA Rose-Hulman students, we don't know it, but it is a surefire, it's not a thing, at this moment, it is a given number. And if I collect sample data, I'm going to get an estimate with X bar and then try to, net the true mean mu with it. So on average, we would expect 95 of them to contain mu. But some of them's not. You're always going to get that sample that doesn't, even if random and done correctly, won't contain mu. Okay, so I hope that makes sense. And I wrote an example here, again, just another one that no matter what you're saying, you may not. And so, you may not capture mu. So here's a population whose true mean mu was 50. somebody built, again, took random samples from the distribution, had a mean of 50, built a confidence interval, and noticed that some of them don't contain 50. I mean, that's what's going to happen. This was just an example saying, you know, if, again, I have a confidence interval right here that says, I was trying to figure out the true mean GPA, not GPA, earnings of college students over the summer. Government says mu is 4,500. I grab a random sample of 100 students, get this, build an interval, get this. I'm 95% certain this contains the true mean earnings of college students over the summer. The government said this, we're in contradiction. So either there's a 5% chance my interval doesn't contain mu, or somebody's not telling you the truth. But we know the government always does, so okay, sorry, I had to throw that in. Okay, so I think that's a nice example, and I'm going to stop it here and start again later. And actually I better plug in soon to get more power. There it is. I have 14 minutes. Yay. Okay, talk to you later. Hi, I'm finally back from California, and I haven't made a video for a couple days, so I'm a little bit, I might be behind you, or I don't know where you are. You might be working on the test right now. There's just a little bit left in the class, but I think the last really major thing is doing some type of statistical application now that we understand probability a little bit better. And some of the things we did with the central limit theorem really leads us nicely into this section. We try to fit in a statistical application just because some of the departments that require the probability class want their students to see some type of statistics in the course, and this I think probably is the most relevant given what we've already built up so far in the class. So here's a nice comic. Obviously we got to start with that. So let's come down a little bit. So I'm just going to define a little bit about statistics, a little bit of background, and then I want to build a confidence interval. So statistics is a discipline concerned with, this is a big word, optimal acquisition of data. This is not an easy task, getting good data, good random data representative of your population. If you take in bad data, your results are not going to be worthy of even displaying. So optimally acquiring data and then analyzing it in order to model some type of situation. And a lot of probability, we use those probability models to model a population to make predictions about the future. Statistics has two branches. If you were to take 223 or an AP Stat course, part of it is just doing descriptive statistics. This just means you collect a set of data. So maybe I'm collecting data on GPAs of Rose-Hulman students. So let's say I take a random sample of 10 students, and here's some of their GPAs. I'm just making up numbers. I don't know. I'm not quite there. Let's just say I randomly sample, get 10 values. If I'd like to describe this data, that's called descriptive statistics. So you can describe it with values. Little x bar for us is the mean of a sample. Little x tilde is the median value, the middle value, and then you line them all up. Little s is the standard deviation. There's lots of measures you can find with a set of data. R is the range, the max minus the min. So we can also do graphics, right? I could maybe make a histogram and say whose GPA, how many are between 1 and, I don't know, maybe 1.5, 1.5 to 2, 2 to 2.5, right? And then you've probably seen histograms look like, kind of look like these bar graphs, right, that show how many are in each category. So there's lots of ways to display data as well. Many types of graph, and there's a nice statistical package. You'll see it down. You probably see it in my window, Minitab. We'll use that in a little bit. The kind of statistics that we're going to talk about for our application is inferential statistics. you collect a set of data and you try to infer something from the sample about your population. So first of all, a sample is just a subset of the population. So imagine this is the whole population. We could just say Rose-Hulman students could be our entire population. And I want to take a nice random sample. That could be stratified sampling, systematic sampling. There's a lot of ways to take samples, but you want to make sure it is random. So let's say we take, again, before I took 10 students. No. No. And then this is my sample. And then from that sample, let's say that the sample I had above, if I average those 10 GPAs, let's say I had gotten 3.17. Now this is only a random sample of 10, but how well does this represent the mean of the population? So all quarter we've been working with populations and population distributions. You've seen the Greek letters, mu, sigma, I don't know what else we've used, well, alpha, beta, anything that's Greek represents the population, but this is just the mean we got for the sample. Mu would be the mean for the population. So is this a very representative value of the mean of the entire population of students? If I took every single student at Rose, there's about, I think there's about 2,000 now. And let's say I averaged all 2,000 GPAs divided by 2,000. Is 3.17 a good indicator of what the true mu is? I mean, we could find mu if we could talk to the registrar and they give us every single GPA, but probably the best we can do is get a random sample and then try to infer how close to the true mu we are. So one value alone doesn't do a very good job at representing an entire population. And again, with a population, you're usually looking at parameters. I always say, like, what's the parameter for the exponential? You're talking about a population value. Sample statistics are usually given by, I want to say, alphabetical letters, not mu and sigma. And populations are given by the Greek letters. A sample mean, X bar, can be quite different from the population mean mu. So we had gotten for 10 randomly chosen students the GPA of Rose to be 3.7, but mu, I mean, maybe mu is, I'm just gonna make up a number, 3.35. I mean, I don't, there's some question about how good this is. This is only a sample of size 10. Of course, if you take a bigger sample, we could get closer to the true mu, but there's some probability involved with how good this is. So instead of just giving you a single number, what's a little bit better than to give more precision is to build actually a confidence interval. So maybe instead I have an interval that says I'm 95% sure that the true mean GP at Rose is somewhere between 2.8 and 3.25. Again, I don't have just one number, but now I feel a little bit like this is more reliable. Again, I didn't tell you how I built it, but right now I'm just saying I'm 95% certain that this interval contains the true mean mu. And that's what I'm trying to do with that confidence interval. I'm trying to give some confidence to this interval of numbers that I hope contains the true parameter of interest I'm looking for. So this is what we call a confidence interval. And the main thing about getting it is we need a random sample. And in this class, I'm just going to build one for mu right now. We can build a confidence interval for any parameter you want. We could build one for sigma, the standard deviation of GPAs. Anything, the true median of GPAs. I mean, you can build a confidence interval for any parameter you want. And the confidence level tells you the degree of reliability of the interval. So of course a 95, I'm more confident with this than a 90%. But the thing is, with a 90%, we can actually get a tighter interval. So maybe now this is 2.9 to 3.21. I mean, yes, I've lost some confidence, but I've gained a little tighter interval. So, I mean, I always joke too, I mean, we could have a 100% confidence interval. I'm 100% confident that the true mean GPA of Rose-Hulman students is between 0 and 4.0. I mean, that's a useless statement, but I'm 100% confident in that interval. So I wanted to go to Minitab and build a couple confidence intervals for you so you get the gist of how I'm making them, and then we'll do some problems. But I think I'll just stay with a short video for now.